This is ECE 343 Signals and Systems. This will be the third part of Chapter 4. In the previous two parts, we looked at the bilateral and unilateral Laplace transforms, as well as some properties of the Laplace transform. Today, we're going to spend most of our time talking about the solution to differential equations using transform domain techniques. We have spent a bunch of time back in Chapter 2, for example, solving constant coefficient linear differential equations using time domain techniques. We would like to see the kind of advantages that a transform technique might allow us on that. In order to do that, I'm going to revisit a circuit that we had seen back in Chapter 2. So if you go back and look at Chapter 2, Part 2 lecture, you'll see an op-amp circuit in there. I'm going to repeat it here. And rather than solve it using time domain methods, we'll go ahead and solve it with the transform domain methods. So let me go ahead and draw out what that circuit is. It begins with a voltage source. So we have a voltage source sitting over here, and the voltage source is going to pass through a resistor. I'm going to go ahead and keep the same sort of assumptions that I had when we analyzed the circuit previously, which is I'm just going to go ahead and let these have unit component values. So we're going to have a resistor there that is 1 ohm, and it's going to come into a node, and there will be another resistor, and that other resistor is also going to be set at 1 ohm, something along those lines. And then that's going to hit another node before going into an op-amp. So we're going to have an op-amp circuit in here, and it's going to go into the negating terminal on the op-amp. The non-inverting terminal is just going to be tied directly to ground. Going back to the first node in there, we're going to go ahead and run a capacitor straight to ground. So we're going to have a capacitor in there, and I'm going to let that be a 1 farad capacitor. And then I'm going to put a resistor coming off that node as well, and that's going to be another 1 ohm resistor. It doesn't have to be this way, just make a convenient set of values. And then I'm going to allow that resistor to be connected to the second node that we had also through a capacitor. So we'll go ahead and put a capacitor in there, and we're going to let that be 1 farad. And then that top node, we're going to go ahead and let that make the feedback path all the way to the output of the op-amp, and go ahead and tie those guys together. And the output of the op-amp we're going to take as our output voltage. So Y of t coming out of the op-amp is going to be our output. So this is just a simple op-amp circuit. It has 2 energy storage elements, right, the capacitors, and then 3 other resistors in there. We had analyzed this previously for the case of R equaling C equaling 1, and we came up with a differential equation description for this guy. Rather than go back through all that analysis again, you can go view that through Chapter 2's Part 2 video. We know that the differential equation describing this circuit is going to be a Y of t plus 3 times the first derivative of Y of t, and then we're going to have plus the second derivative of Y of t, this whole thing being equal to minus X of t. So that's our differential equation description on this, and what we'd like to do is we'd like to give it some conditions for which we're interested in solving it. So let's go ahead and do the following. We'd like to find, in this particular case, I'd like to go ahead and find the total response. So I'll call this Y total of t, right, with the following conditions. I would like to go ahead and set the input equal to a unit step function. That's like putting a 1-volt battery in the input of the circuit. And then I'm going to also allow there to be some initial energy stored in this circuit across those capacitors, if you will. But I'm just going to write it in terms of the standard initial condition. So I'm going to do it in terms of the output variable, Y of 0 equaling Y dot of 0 being equal to 1. Let's just allow it to have those 2 initial conditions both equaling to 1. So what do we have? We have a op-amp circuit, 2 energy storage elements, right? We have a differential equation description for that, which we could have gotten through something like Kirchhoff's voltage laws. It's a second order differential equation, as we would expect, right? That second order differential equation, the fact that it's second order conforms with the idea that we have 2 energy storage elements. And then we have some sources of energy. We're applying energy through the input in the form of a unit step function. And then there was also some initial conditions, which would be reflected in the voltage states of those capacitors, that translated to Y0 and Y dot 0 both being equal to 1. So I would like to go ahead and solve this guy. If we had done this with a time domain method, right? So I'm going to just do a very, very quick recap on this, that if we looked at this particular guy in the time domain, so let's just go to say time domain solution. The time domain solution. And just remind ourselves how we would do that. We would say something like this. We'd say y total, right, would be equal to, we'd have a y0 input response, right, plus a y0 state response, something along those lines. When I look at that y0 input response, I know that that's going to be a sum of modes. So I would have to go ahead and I'd have to take a look at that differential equation, find the characteristic polynomial, find from that characteristic polynomial the characteristic roots, use those characteristic roots to find the characteristic modes. I would have to weight each of those modes with an unknown coefficient that we would find through application of the initial conditions. So we did that all back in chapter 2. The zero state response, right? We know that that guy is going to be basically the impulse response, h, convolved with the input. So I'm going to need a convolution in that. In order to carry out that convolution, I'd have to find the unit impulse response h, right? And that h had kind of an ugly form. So we had some form that we memorized. It could maybe have a delta function. It had something that looked like a zero input response, but we had to use different initial conditions to find the coefficients for that zero input response. And then we had to apply PD onto that guy, combine it all together. That just got us the h of t. Then we had to go through a 3-step method in order to carry out the convolution. And then you ended up solving the total response by just adding those two pieces together. It is a time-intensive, and I'm going to say somewhat awkward kind of method. What we would like to do instead is we'd like to engage in a transform domain or a frequency domain. So I will call this a transform domain solution. Let's go ahead and look at the transform domain solution instead. I think this one should be a lot easier. And basically what we're going to do is we're going to employ the unilateral Laplace transform. The reason that I would like to use the unilateral Laplace transform rather than the bilateral Laplace transform is because I have initial conditions that I need to be incorporating into my overall solution. So I might just put a little arrow here, right, to that unilateral part, and note that we choose, right, we choose in this particular case, we choose this unilateral version, we choose the unilateral version, right? Since we have initial conditions that we want to incorporate. So what do I do as a starting point? I'm going to go ahead and grab that original differential equation again, and I'm going to put it into standard form, and I'm going to go ahead and use an operator form on that. So if I go back to the differential equation, it looks something like this. I had a d squared plus 3d plus 1, right? That thing acting on my output variable y of t, right? Being equal to, and I had on the other side a minus 1, so a minus 1 acting on x of t. That minus 1 was my PD. It's kind of a boring one in this particular case. And then I am going to be sitting there and taking the unilateral transform, the unilateral Laplace transform of that entire differential equation description. So rather than spending any time whatsoever in the time domain, we're going to go immediately to the frequency or transform domain, this S domain. Okay, so first operation, that unilateral transform, we know a unilateral transform is a linear operator, so I can take the unilateral transform of each piece and just add them together. The first piece in there is the second derivative of y of t, and so I need to be able to go ahead and take that guy's transform. I know that the second derivative of a variable, right, gives me what? That's going to give me an s squared y of s, right, something like that. But then there's some conditions or some dependence on the initial conditions. And so I'm going to get a minus s times y at 0, and then I'm going to get a minus y dot at 0. And those dependence on initial conditions you can certainly find both in the book and in the formula sheet that's put on Blackboard on the class website. And just as an easy reminder of how that derivative operator, the derivative property for Laplace transforms, and especially the unilateral Laplace transforms work out. So that was the first term. I'm going to do this kind of separate lines because these get a little bit long. And so the next one is what? And maybe we'll color code this just a little bit. So we took, right, this d squared, right, acting on y of t, and that gave me this piece right here. Right now we're going to go ahead and we're going to be doing the 3d acting on y of t and see what we get on that. So the derivative of y of t, right, is going to give me what? It's going to give me an s just to the 1, right, because it's a first order derivative. And then I get my y of s, and then there's going to be dependence on the initial condition. So I get a minus y of 0. But then there was that 3 out front, right? 3 times that. So 3 operates on that entire derivative operator. So I should be getting a 3, and I'm going to put my parentheses here around that entire part that was reflective of the derivative. A common mistake that I see is that sometimes people take that 3 or whatever that constant is out front, and they'll do something like 3s y of s, and they'll forget to multiply that 3 times the initial condition. That 3 is multiplying the entire derivative, right? And so whatever the derivative transforms to, including that initial condition, you also have to multiply the 3 on there. So I'm using the derivative property of the Laplace transform as well as the linearity property of the Laplace transform. And so I get some terms in there as well. Remember, these guys are getting all summed up. The last one is just the Laplace transform of the signal by itself, y. So we probably don't need another line for that, so I'm going to go ahead and put y of s. If I wanted to go ahead and color code that, I could do that as well. So we know there's that term 1, and we end up getting this piece over here, y of s, something along those lines. I now need to go ahead and transform the other side. The other side is an easy transform as well, because the PD here is just so trivial. It's -1. So the unilateral Laplace transform of minus x is just going to be minus cap x now as a function of s, something along those lines. So I'm starting to get somewhere on this. What I would like to do is I'd like to do a little bit of term collection and also perhaps substitute in what is the transform for x, because we knew what the time domain function was. It was just the unit step function, something along those lines. Let's first collect our terms together. I'm going to collect everything that has a ys in it. And so I'm going to look at those first. I'm going to have an s squared y of s. That's from that blue underlined piece. And then I'm going to have a plus 3s y of s, right? That's from the red term. And then I'm going to have a plus y of s. That's from the green term. And then I'm going to have some stuff that depends on those initial conditions, right? So I'm going to have a minus s little y of 0, and I'm going to have a minus y dot at 0, right? And then I'm going to have a minus 3y at 0, right? And that takes care of all those initial conditions. And then I'm going to have on the other side here a minus x of s, something along those lines. Okay, so excuse me, we're trying to do some further simplification here. But before I do that, I would just like to point out a couple of components in here. We have all the output terms collected together. So let's factor out that output term, right? And then see what multiplies it. And it is a straight multiplication in this time. I'm going to go ahead and factor the y of s term out to the right. So I'm going to leave y of s here factored out. And what did we need to multiply y of s to get those 3 terms that all have y of s? Well, I need an s squared plus 3s, right? Something like that. And then I'm going to have a plus 1. If you're paying a little attention to the original guy, right, you might notice this first piece in here, right? This first piece is just that q, right? It's that q polynomial from my original differential equation, replacing d with s, okay? So that's just q of s, and this happens every single time. So that characteristic polynomial we saw in the time domain is equally important. It's equally prominent here in the transform domain as well. We get qs y of s, something along those lines. I now need to go ahead and think about those initial condition terms, right? And so I could do something like this. I could bring them to the other side, which I'm going to do at this point because eventually we're going to solve for y of s. So I'm going to go ahead and set this whole thing as being equal to, and I know that there was some y of 0 terms, and there were 2 of them, and so I can just factor some things in here too. Y of 0 had an s and a 3 in it. The minus signs are going to get changed to pluses when I bring them to the other side. So I'm going to have an s plus 3 in there, right? And then I'm going to be a plus y dot at 0, something along those lines. So those were all those initial condition type terms that were on the left before, and now I brought them over to the right. And then I have in here a minus x of s, something along those lines. Okay, so a little bit of noting here as well. If I take a look at all of this stuff here that has to do with y at 0 and y dot at 0, these are all initial condition dependent terms. These were all initial condition dependent terms, right? And then the last piece over here is all stuff about the input. So it's an input dependent term, right? So we have something about the output being equal to something that depends on the initial conditions and something that depends on the input. We're going to make more use of this in a moment. All right. I do need to know what the transform of x is. So we had x of t as being equal to u of t. And I would like to unilateral transform that guy to get my x of s. Now there's really a couple ways you could probably do this. If you wanted to do it probably most simply, you could just consult a table of Laplace transforms. That's certainly doable. I'm going to just go ahead and do it by hand calculation here. So I'm going to get my x of s as being an integral of my x of t. X of t is just 1 between 0 and infinity, so I'm going to get limits here going from 0 to infinity. And then I'm going to get 1 times, well, that exponential that's part of that Laplace transform definition, so e to the minus st dt, something along those lines. Go ahead and do that calculus in there. I get an e to the minus st over minus s going from 0 to infinity, right? As long as this thing converges, this was a right-sided signal, the root is at 0, okay? So we're going to have a region of convergence that is the real part of s being greater than 0. And if that's the case, that infinity term goes to 0, and I'm going to have minus then, and I'm going to have e to the 0. That's just 1, so that's going to be a 1 over minus s. This whole thing, right, as long as that initial condition was held, that's not such a great copy of that. Let's go ahead and do this. As long as that initial condition term, right? As long as that initial condition term was satisfied, we end up getting this overall transform then being a minus of a 1 over minus s. That's just 1 over s. Now you could go consult the table of common Laplace transform pairs in the book or on the formula sheet in the class section of the course website, and you'll see indeed that u of t does go to 1 over s. Okay, so I'm going to take that result and plug it back into this equation. Let's go ahead and make a copy of this guy. I'm going to do so without all of those explainers down underneath. So we'll go ahead and grab this guy. We're going to go ahead and copy it, and we're going to bring it back down and replace, and go ahead and start continuing our simplification on this guy. So in this particular case right now, I know that in this expression, I can do some further simplification by noting that this guy is 1 over s, right? And what else do I know? I know that my initial conditions were both 1s, something like that. So I'm going to do just a little bit more simplification, and I'm going to say my y of s. And notice what I'm doing here, right? I've had a little bit of transform effort to go on here, but I haven't had to do any calculus really. I could have certainly avoided it. The only calculus I've needed so far was in taking that Laplace transform of x, and that I could have gotten by table. But I'm sitting here and by and large solving this differential equation by using algebraic rules, right? I factored out stuff like these s squared plus 3s plus 1 terms. Those were all reflective of derivatives, right? S squared just means second derivative. 3s means 3 times the first derivative, and then 1 is just the signal by itself. We know differentials in the time domain can't be pulled from the variable of interest. That's why it's hard to solve them. Here, they become a straight multiplication, and that straight multiplication allows me to start algebraically solving this expression. So I'm going to go ahead and solve now for y, right? I'm just going to divide both sides of the expression by that s squared plus 3s plus 1. And I'm going to do it after I've made these other substitutions as well. So what was y0? It was 1, and y dot at 0 were both 1. So I'm going to get an s plus 3 plus 1. That's going to be an s plus 4. So if I have my, oops, let's do this back in our black here. So we're going to have s plus 4, right? And then we were dividing by that term on the right, and I'm going to get an s squared plus 3s, right, plus 1. You might wonder why I'm putting those little serifs on the variable s here. I do that very intentionally, or at least I try to do it intentionally, because s's are oftentimes easy to mix up with the number 5, and I definitely see that as a source of error. People will go along and maybe be just a little bit sloppy in their writing, and they'll make an s a 5 or a 5 an s, and then your answer really goes off the rails. So I try really hard to make sure that I can identify what things are s's and what things are 5s. I'd encourage you to do the same. Okay, so I've got all that stuff to do with the initial conditions, and so I'm going to remind us again down here, right, that this guy here is all to do with initial conditions. The only reason that term is there is because of the dependence on initial conditions. And then I need to add in this last piece. So I had a minus 1 over s, but then I was also dividing by an s squared plus 3s plus 1. So I'm going to have a minus 1, right, over, in this case, and I'm going to have s times s squared plus 3s plus 1. And I would just like to note, right, that this whole thing has only to do with the input. Now I'm going to just look at this for a minute and think a little bit. I'm going to do kind of an aside. I'm just going to say recall, right? Recall from our discussions back in chapter 2 that y total, right? Our total response for system could be y, right? And we had zero input response, right? And then we had y and we had zero state response, right? The zero input response depended only on the ICs. The zero state response only depended on the input. So actually, if we just are careful here, we don't get too uh, um, excited about recombining terms. If I maintain the separation of those parts that came from the initial conditions and those parts that came from the input, I could actually use this to identify, right, that this piece here is actually the transform of y's zero input response as a function of s, right? Linearity says the time domain expression in the transform domain has the same structure. The y total is going to be y zero input plus the y zero state. So the second part here, right, this guy is going to be the y zero state response of S. So if you had a need to maintain separation of those guys, you certainly could do so. You could certainly maintain separation. For this particular one, it only asks for the total response, so I don't think we have to have a separation. And so I'm going to just go ahead and combine those terms right now. You could combine the terms after you did partial fraction expansions and after you did the inverse transform, but just for kind of illustrative purposes, I'm going to go ahead and combine them together now. So what I would like to do is I'd like to take my expression for y of s, and I would like to represent it as a single rational function. You'll notice that the term on the left has the denominator s squared plus 3s plus 1, right? So we have that s squared plus 3s plus 1. Well, so does this right-hand term. It has an s squared plus 3s plus 1, but it also has that extra term, right? It has that extra term s. So if I want to combine these together, right, I need to multiply this first one by an s over s. That's just a fancy one, and it's going to ensure that they both have the same denominator, and then I can combine everything together. So if I go ahead and I do that, I'm going to get y of s then being equal to, and I'm going to go ahead and make this as a single denominator, and it's going to be s times, and I'm going to have s squared plus 3s, right, plus 1. And then what do I have in the numerator? I'm going to have an s squared plus 4s, and then on the other side, I'm going to have a minus 1. So in that particular case, I should have an s squared, right, plus 4s, something like that, and then a minus 1. So this is an expression. It's a rational function, right? A rational function expression. This is very common for differential equations. I'm going to get this rational function expression that describes my total response, y, in the transform domain, so y of s. To get the solution I need to inverse transform this guy. So I do have those extra steps when I do transform domain analysis. I have to take both the forward transform and I have to take the inverse transform. The advantage, though, is that in between those two, right, I just have algebra to deal with instead of all that other stuff we did back in chapter 2, the convolution and all that other kind of just difficult to remember stuff. Notice here, too, I'm getting a solution, and I never explicitly found the unit impulse response, right? It's just coming through in the math. We never had to explicitly find h of t. We aren't going to have to explicitly do the convolution. We just have to do some algebra in here. So that's actually really nice. I would like to make one comment, though, before we go ahead and do a partial fraction expansion, is I would like to look at this denominator for just a minute. I have definitely seen people, and so I'm going to draw this in red. I'm going to do it in red because it's something I see, but it's something that I think is just one of those unnecessary steps that's likely to cause you more problems than good. So some people here would like to turn this guy into, the most standard form rational function possible. So they'll write this as an s squared plus 4s, right, minus 1, really no problem at this point. And then they say, oh, well, that thing down on the bottom has partly an expanded form and partly a product form. Let's just multiply it all out. So I get something like an s cubed, and I'm going to get a 3s squared, right? And then I'm going to get an s, something like that. Now, there's nothing wrong with this. You can do this. There's no mathematical, errors being committed here. But what's the first thing that I need to do when I want to return this guy to the time domain? I want to carry out a partial fraction expansion, and so I'm going to want to take this original proper, or yeah, it is a proper one, I'm going to want to take this original rational function, and I want to do a partial fraction expansion on that, right? I want to do a partial fraction expansion. And the first step on that partial fraction expansion is to root out the denominator. And in its current form, the way I have it written right here, where that s is pulled out front, I've already started that factoring. If you multiply it out like you got over on the right-hand side here, right? Now it's something like, wow, I've got to figure out how to find the roots of a cubic, where on the left, I've already got that partly factored, right? And at most I have to find the roots of that quadratic out there. So sometimes when you multiply things out, right, you're actually going to make the rooting problem of finding that partial fraction expansion more difficult. So we're not going to do that. We're going to just work with this first expression of that rational function, the one that is underlined and greened in there. And I'm just going to sit there and say that we need to root this. Well, let's do that in a different color. So let's go ahead and think about we want to root. Let's find the roots of the denominator. And you can do that with your favorite method. You can use a quadratic formula. You can use MATLAB, whatever the case may be. I'm not going to repeat that here. I'm just going to give the solution. That chapter 2, part 2 lecture again provided how to handle the original roots of that characteristic polynomial Q. Notice, right, this guy right here is just my Q, right? That is my Q sitting in there. So my solution to this differential equation is going to highly depend, right, on those characteristic roots of my system. That's no surprise. The characteristic roots of the system tell you, right, how the system wants to respond to energy. There is no surprise whatsoever that when you stuff energy into the system, either through initial conditions or through the input, that it's going to respond with those modes there that are characteristic to the system. It's built in. It's built in for it to do that. Going back here, we do see that we get a root, and I'm just going to call this particular root lambda 0. That is equal to 0. We have a lambda 1. I'm going to go ahead and write that out. That's minus 3 plus root 5 over 2. And I have a lambda 2 in here. So I'm doing a little bit, I guess, different numbering. Maybe you wanted to go lambda 1, 2, 3. It doesn't really matter. I get 3 of these guys. So I'm going to have lambda 2 being minus 3 minus root 5 over 2. So one of them is pretty easy. The other two are a little bit messy, okay? And what I would say is that in this particular case, I would probably turn to MATLAB to go ahead and set these guys up and carry out the calculation. So I do the PFE, so I'm going to just say PFE is going on in here, right? And what does that tell us? It tells us that y of s can be expressed not as a single rational function, but as a sum of a lot of lower order rational functions. And so we get something like, right, we get some coefficient over the first term, which is s minus 0, so I could just write that as s. We're going to get some other coefficient. I'm going to just call that b for right now, and that's going to be s minus our lambda 1, and I'm going to write it as lambda 1, because who wants to stuff in all that mess, minus 3 plus root 5 over 2? Just do it symbolically. And then I get that third coefficient, which I'm going to just call c for right now, and that's going to be s minus lambda 2, as I've written it right now. And again, I'm not going to substitute in what is lambda 2 right now. I can use you can use whatever favorite thing you want. So I'm just going to use the method of residues. This is something we've already covered, so I'm not going to do the details. You could use something like method of residue, whatever is your favorite method. You could use MATLAB's residue command, right? You could find a common denominator here and equate like coefficients. Lots of different ways of finding these coefficients, A, B, and C. I'm just going to go ahead and give the results out here. You can check this on your own. It would be a good check if you're feeling a little bit rusty on this. And what we find is that we get A equaling minus 1, we get B equaling 2.79 and change, and then we get C being equal to minus 0.79 and change. And for this point, I think these rounded values are good enough. So let's rewrite our transform solution, y of s, with those coefficients put in there. I'm going to get a minus 1 over s, right? And I'm going to have a 2.79 over s minus lambda 1, and then I'm going to have a minus 0.79 over s minus lambda 2. And if you really wanted to, maybe we can do it this way, right? This first one is an s minus 0. All of these are simple roots, s minus something, right? And the something is the root. It's either 0 or lambda 1 or lambda 2. I just need to do the invert transform now. So I'm going to go ahead and take this guy, right? And I'm going to do the inverse unilateral Laplace transform on that guy. That on the left-hand side is going to give me y of t. And then when I start looking at these other terms, I can get this straight from the table, right? These are all simple terms. These are the ones that we've already worked with before. The first one is just going to be what? It's going to be a minus 1 times u of t, so a minus u of t. We had already seen that. X of t was the unit step. We had computed its transform as 1 over s. Transform pairs are unique, so 1 over s must have come from a u of t. So the first term in there is a minus u of t. The second one is going to be 2.79, and I'm going to have an e, right, to the lambda 1t u of t. And if you wanted to, you could plug in what is lambda 1. It's a negative real number, which is actually a good thing, right? That means that this thing wants to bleed away energy. It's going to have something to do about the stability. All those conversations we had before are still holding true. And then I'm going to get a minus 0.79 here, e to the lambda 2t u of t, and I am done, right? This is my final answer. So think about what we had to do process-wise to get this answer. Yeah, there was some math, right? But the math itself is probably a whole lot more simple than what we would have had to do for a time domain solution. We looked at the circuit, right? We took a look at the circuit and we found a differential equation. We noted what the initial conditions and input were. We didn't want to mess with this in the time domain, so we went ahead and took a Laplace transform and did a little bit of algebraic simplification, right? Ended up getting an algebraic type solution on that guy. Transform the input, input the initial conditions, and solve for y of s. That gave us a simple expression that was just in terms of rational functions again, because I was only looking for, at this point, I could have separated out the zero input and zero state if I wanted to. I could have just inverse transformed each of those two pieces separately. Because that wasn't asked for, I combined them together, got a single expression, did a partial fraction expansion on that guy, right? And then just invert transform using tables. Very, very straightforward, very, very simple kind of process. And one that I hope all of you can appreciate or recognize as being just much more likely to provide a rapid path, an efficient path, and one less prone to errors, right? This transform domain solution has got a lot going for it compared to doing all the stuff that we did with time domain solutions. Okay. So let's look at a couple other pieces in here as well. I'm going to do a few loose ends on this thing h of s, which we call the system function. So let's go ahead and look in this particular case, and I'm going to call this loose ends, right, on h of s. And h of s goes by a lot of different things, right? So what are some different things that we know about h of s? H of s we had seen before, and we had seen it called the system function. Okay, so that is one thing that it's oftentimes called. It is also called the transfer function. So these are just both transfer function. These are both common terminology used to describe this thing h of s. And what was h of s? It was the Laplace transform of the unit impulse response h of t. That's certainly one way of interpreting it. So we could think of this as the Laplace transform of h of t, right? We had also seen it in this sort of context as well. We know that it was something like, if I took an e to the st into my system, right, out pops e to the st times that h of s, right? So we had seen it in that way before. In our previous lecture, we had also seen it in something like this. We said h of s, right, could be gotten as the zero state response, right, over x of s, output over input in the transform domain. So that was another way of carrying this out. I would like to come up with just one more mechanism for probably computing out this h of s, and one that's probably the simplest of all of them. And so let's go ahead and take a look at just one more. What do we know about the zero state response? The zero state response says all the initial conditions of my system, y at 0 and y dot at 0, right, all the way out to however many derivatives we need. So this is going to be the n minus 1th derivative at 0. All of those guys are equal to 0. We're going to assume a causal input because we're dealing with a zero a state kind of response here. So we're going to look at a causal input, and with that causal input, we know x of t equals x of t times u of t, right? It doesn't have anything starting before 0. And what this tells us as well is that x at 0, just a little to the left, that's that 0 minus. It's just a hair before 0. You can read the book about the kind of technical details of this distinction. I think at this point it's not something that we have to highly get too hung up on. But that's going to be x dot at 0, and going on as many as you want, all of those are going to be 0 as well because the input was causal. What does that tell me? That tells me that if I unilateral transform, right, my original differential equation, QD y of t being equal to PD acting on x of t, right, what do I get out of that? Normally, you would get some powers of s multiplying either y or x, right? The power of s depending on the power of d. And then you would have that mix in of all the initial conditions. But we've established here that all the initial conditions, right, are 0. And because we're talking about causal input, all the what you might call initial conditions on x are also 0. So this transform under this condition is super simple. We just get q of s times y of s being equal to P of S times X of S, something along those lines. Now, this was for what? It was for my zero state response. We had already said that. So we were looking at the zero state response, right? We knew that all the initial conditions are 0, and we were applying a causal input. That's what you do in this case. And so we're going to go ahead and put a causal input. That gives all these guys in here. And we're solving for the zero state response if you want to think about it in that way. So what is that zero state response going to be? I can solve that. Y zero state response of S, right, is then going to be P of S over Q of S, right, times X of S, something like that. But we also know, right, we also know because we had a time domain expression that said y zero state response equals what? It was equal to h of t convolved with x of t. And if you transform that guy, you get y zero state response as being h times x, something along those lines, right? We can go ahead and do that, and we would recognize then that this guy is h of s. Another way of doing this is we wouldn't have to use the unilateral transform. We could just use the bilateral transform, and the bilateral transform with its, and that might actually be a cleaner way of doing it. The bilateral transform derivative property just gives us powers of s. There are no initial conditions to worry about because you could be talking about signals that extend from minus infinity to infinity. So if you don't like this kind of minor assumption that I did here of a causal input, you can get exactly the same result by just applying the bilateral Laplace transform instead. So it's really not a big problem in either case. So what do I end up getting then? I get this really nice idea about another way that I can get h of s, right? So from this, I guess I can go ahead and conclude that that transfer function, that system function, that h of s, which is the Laplace transform of the unit impulse response, right, can just be gotten from my original differential equations, right? Polynomials, P of S by Q of S. This is a great expression, right? If I have my differential equation, right, getting the system function or transfer function is trivial because all of those things are going to be built directly into it. So as an example, we just looked at a circuit, right? This circuit looks something like this. We had a d squared plus 3d plus 1, right? Times y of t being equal to minus 1 x of t. Shouldn't have said times, I should have said operating on. So d squared plus 3d plus 1 operating on y, right? So operating on that y equals minus 1 operating on x. And we had noticed before that this guy here is my q of d, right? And this piece over here is my p of d. From what we just learned, right, we can get the system function, the transfer function for this system, h of s is being equal to p of d over q of d. So p of d over q of d, right? And we know that here is minus 1 over, and I'm going to have, and I should not have had d's in there. These are s's. So let me fix that very quickly. So that's going to be p of s over q of s. Something along those lines. And that's going to give me a minus 1 over, I'll just replace the d's with s's. I'm going to get an s squared, right? And I'm going to have a plus 3s, and I'm going to have a plus 1. Okay, so really, really fast and simple way to get this transfer function. Now, if I wanted to get the h of t, right, h of t, I would just take the inverse Laplace transform of that guy, minus 1 over s, and I forgot my squared up there somehow, s squared plus 3s, right, plus 1. How do we do that? Well, it's a standard type of stuff, right? Do your partial fraction expansion and use your tables. This mechanism of getting h of t is just way simpler than what we talked about back in the time domain. If you remember back in the time domain, we did something like this. We said something along the lines of, we can go ahead and get, just as a reminder, right? We said, h of t could be something like a b0 delta t, right? Plus some pd acting on something that's a bit like a zero input response of t. That whole thing made causal u of t, and you had a whole bunch of work to do in that. There were some sort of specialized C's, right? So we had some special initial conditions, which weren't so easy to figure out where they came from. You had a whole bunch of extra work here in applying that PD. You had to remember the exact form of the differential equation to know if that delta function's in there. And then you had to do all of that math in order to get the overall desired thing, which was that h of t, right? Here, it's simple, right? I just take my differential equation in standard form. It's P of S over Q of S, and I do my standard partial fraction expansion inverse Laplace transform, and I get the h of t. You don't have to worry about special initial conditions. You don't have to really worry about explicitly finding the characteristic roots, although they're going to be there, right? Because this denominator is Q, and we know the partial fraction expansion involves what? Rooting out the denominator. So that's rooting out Q. That is finding the characteristic roots, right? So we can see how that comes in automatically. All the coefficients, though, right, come through that partial fraction expansion, breaking that thing up. And that is just way easier than all the mess that we had to do previously. So my expectation is that the vast majority of people in the class, as well as the vast majority of engineers who are trying to find this impulse response, are not going to do it through time domain techniques. They're going to do it through a transform domain technique, right? We are going to get that transform domain technique and get our h of t much simpler. So a couple of final comments on this then. We can say what? We can say the denominator, denominator, yep, we can get that in there. The denominator of our system transfer function, or the system function h of s, is q of s, right? What does that tell us? That tells us the poles of h of s, right? What are the poles of h of s? These are the values, right? The values of s that make h of s, right, go to infinity. So it's basically the roots of the denominator, right? So the poles of h of s are, right, they are the characteristic roots. They are the characteristic roots. Characteristic roots of the system, right? And we can find that by saying, q of s being equal to 0 and solving, right? We can find them that way. So we can certainly find that. We can find it as look at, right, at the roots of the denominator of h of s. And because we know that these characteristic roots, right, establish things like the stability of the system, we can look at the system transfer function, not only to get us that h of t if we want, but we can also use it to establish information about the stability of the system. So let me just state that as well. So we could say, therefore, the poles, right, the poles of h of s, right, help us establish the stability, right? The stability of the system in exactly the same way that we had talked about way back in chapter 2. If all your poles are in the left half plane, you got an asymptotically stable system. If even one is over in the right half plane, you got an unstable system. You can tolerate unrepeated roots on the omega axis, right? That would be a marginally stable system, but if they got repeated, right, then it would become unstable. So all of those things are the same. We can just assess it using this system transfer function, this h of s, right? H of s is kind of one of the fundamental mechanisms for understanding an overall system, a linear time invariant continuous system's behavior. We knew h of t is what we used in the time domain. Here in the frequency domain, we're getting h of s, and we see a lot of things built into h of s. H of s coming back up here, right? If I go back up here, this h of s, wherever I had that somewhere in here, that h of s, right, is going to be the one, this h of s here can be used when multiplied by the input to give us the zero state response. That's one use of it. So we can use it in a multiplicative fashion to get us a zero state response, at least in the transform domain. Because the denominator is the characteristic roots of the system, we can use it to establish the stability. And we could also just invert transform h of s to find that useful quantity, the unit impulse response. If the unit impulse response h of t completely defines the input-output behavior of a system, which we know it does. We saw that back in chapter 2. Because the zero-state response is just the unit impulse response convolved with the input. If h of t completely characterizes the system's input-output behavior, well, then so too does h of s, because h of s is a unique transform, right, relationship with h of t. They are a transform pair. So just as much as h of t was useful for us back in the time domain analysis, h of s is equally useful for us in this transform domain analysis. Okay, so I think at this point, the last little bit I'm going to do, and this will probably be just a bit of a short lecture. We've had a couple long ones, so let's go ahead and make this one short. I'm at a pretty good ending point. Let's just recall, a final recall. So also recall, maybe we could say also recall, okay, that h of s, right, is equal to y of t over x of t in the case that x of t is equal to e to the st. We had seen that before, and I had written it up there a bit. I just want to show it explicitly, that if I put an everlasting exponential into the system, we had done this with a convolution kind of calculation, we got e to the st h of s on the output, right? And so we should be able to take that ratio of y of t to x of t, right? This piece over here is my y of t, right? This piece over here is my x of t. As long as x of t is e to the st, that ratio y of t over x of t, right, would be equal to what? It's h of s e to the st over e to the st. The e to the st's cancel, and I'm just left with h of s, right? So I could get this system transfer function if I could apply an input, an everlasting, that's a little bit tricky, an everlasting input e to the st into there. This is about the only way you could get h of s using time domain expressions. We could say more generally, right? We'd already seen this more generally, right? H of s is equal to the y zero state response, whatever zero state response you have in response to whatever input you want to do, y zero state over x. We'd seen that before. We had also seen that it is p of s over q of s, and really that one is the most likely. Next time, what we're going to do is we're going to take a side path down circuit analysis. So we're going to look at transform domain analysis of circuits, and we'll do some examples of that. We'll then move on to some other interesting topics like system realization, block realizations, and a really important concept coming down the line, something called frequency response. That'll all be upcoming lectures.